So I am a restoration ecologist, and so the ecologist part of that is that I'll tell you something super obvious that you all know, and that is that water runs downhill, and I'll just tell you that over and over again in different ways. It's already off the rails. There we go. So in New Mexico, where I live now, there's a man named Bill Zedyk who's been a pioneer of a lot of these natural-based processes in different systems. He's worked all over the western US. And so Bill has championed these projects that use human labor, volunteer labor in systems to slow and sink water and have it infiltrate in these high mountain wetland systems. So this is Bill. And these are some of his structures that he's had people put out in the landscape. And so I'll keep referring back to Bill on this. And so, of course, Native Americans over time have really used rocks and logs to slow water and send it where they want. So this isn't like new concepts, but Bill has been somebody who's been willing to get out there, tell people that these work, it's simple, explain it, get people on board. And Bill always says that volunteers get paid in feelings. And so he's really big into the benefits that people get from doing this kind of work and having a different relationship with water. Where am I supposed to point this so that it works? There, okay. So one of Bill's projects is in Arizona at the Hubbell Trading Post. And it's a trading post, and so it was huge numbers of Native Americans and pioneers came through, and there were roads and everything, and it was very degraded in the area surrounding. And so when it rained, the runoff just blasted through the wash. And so he started doing in the creek some of these nature-based solutions to slow the water down and make it take a longer path through the system. And so over 15 years, we have the same post in these pictures. That is the effect. And that doesn't mean that it happened in the first year or the second year. There's a couple years where it blew out and they started over again. But it was one of those great long-term projects where people bought into it and they came back year after year. And there's some piezometer wells in the floodplains around, and they actually raised the water table away from the creek, and then they stabilized this creek. And in 20 years, they gained 10 feet of grade back in the bottom of the channel, just hitting it back and back and back. And so this is one of those arid systems where you would think that the progress would be really slow, but the dedication to keep coming back to this was huge. And so I'm going to take you through a system in the Carson National Forest of northern New Mexico, mostly because it's really easy to visualize based on the topography and the vegetation, what's actually happening with the water. It's kind of unique that way. And then I promise you I'll get back to Texas. So these are the kind of structures that we're doing. This is a log mat flow splitter. And then we have a berm that goes out. So essentially what happens in these big wetland systems in the mountains is that a trail or a road right at the toe of the valley slope is where people traveled because it was wet in the middle. And so instead of the creek channel just thrashing through the valley floor as it went along, it got captured by the road and it just shoots out of the system on one side of the valley, drying the other side of the valley. And so we try to, spill some water back out wherever we can and slow it in the system. So that's sort of a typical little build. So this is what it looks like after 2 years. It's the same picture. We have alder coming up, and we actually have achieved a little bit of wetland vegetation where we've spilled it back out. And so this is a wet system, so you get kind of a fast recovery in this system, and it has the wetland plants are just ready to have water again. Okay, so this is where we're talking about, I get to tell you that water runs downhill and has a relationship with gravity. So in runoff, what we want in almost any system is that the rain falls gently enough that it spreads out in a sheet flow situation. Like it's not zooming off the landscape in a channel. And so what all of these little structures do for erosion control and water spreading and sinking and infiltration is that we're affecting the way that the runoff happens on the landscape. So we've got slopes, steeper slopes. Of course, the water is going to run down faster. We have to use a little bit bigger materials for that. But mostly what we're doing is we are changing the roughness of the surface that the water flows over, okay? So if it's a flat surface, the water is going to flow faster. If it has impediments in the way, the water is going to move around the impediments, and it's going to go slower. And so vegetation slows that down. Bill always says that every blade of grass is a little water dam, right? The water will hit a blade of grass. It's going to infiltrate, or it's at least going to slow down. So we are using these rocks and logs as a gateway to growing vegetation in that area that's going to slow the water down the most. And so this is where we're working. So for erosion, there's something that happens to that sheet flow in the system that causes it to go from sheet flow to concentrated flow. And a lot of times, this is what I talked about, it's a road, or it's an animal trail, or even sometimes it's just a big obstacle where water cuts around the edge, like a big rock or something. So it creates this initial nick point, okay? And the nick point becomes a head cut. So the head cut, it's an abrupt drop in elevation at a single location. So this is a step down. So as water flows over this head cut, it's gaining energy right there. So it's got a lot more energy falling over this step when it hits the ground here. So soil starts to come off of this surface, and so head cuts migrate up valley or uphill because the soil is leaving at this cut, and then it causes this down cutting or deepening of the channel. And so as you start this loop, it's a degradation loop, it accelerates, right? So if you raise this, you've got more of a waterfall effect. This is going to deepen faster too. So the water's moving faster and faster through the system. So this is just kind of an eye-catching illustration of what happens with the water on an impervious surface, like a trail or a road. So the blue square is 1 square foot. And so for each inch of rainfall on a square foot of impervious material, you get 0.6 gallons of water in a square foot. So you can imagine if you're sending water off the site, this water is not spreading out over here. It's going off the site and it's taken a lot of soil with it. So anytime we take the complexity out of a system and we straighten things and we send water off the surface as fast as we can, we are robbing all of the surrounding landscape. And so it's sort of an unintentional thing. It's not like the irrigation or the dams that you think about, but think about all of the roads and trails that we have created. And as we break the landscape into smaller and smaller chunks for people, how many more roads and trails we're creating. And so we're drying the landscape by taking water off of it as fast as we can, sort of unintentionally. So this is what a ranch road looks like after the rain. It's even got rapids. You can see how fast the water's moving there. And then cattle trails. So this is moving off-site. This is not infiltrating. It's not nourishing the plants around it. So this is one of these wide wetland valleys. And this is on the Carson National Forest in New Mexico. And the Carson National Forest is now U.S. Forest Service, but it was owned by Pennzoil, and in the mid-'80s, they owed a $22 million tax debt to the IRS, and so they donated it to the National Forest Service to relieve their tax debt. And this landscape used to have about 20,000 sheep every summer and then several thousand cattle. And so this landscape has been used and used and used. And so one of the things about this that I wanted to talk to you about is that this landscape is kind of like a bathtub. These slope wetlands are in these broad valleys. They're tilted down. There's a plug in the bottom, you know, that goes to a bigger river. And so the money that is for these upper wetlands is actually endangered species money, because this is a second-order tributary that flows down to a recreational trout stream that has an endangered trout species in it. And so what we're trying to do is restore these headwater wetlands so that we can tuck the water back underground in the wetland and have it reach the trout stream slowly, and over time it attenuates the flow. And so we are reducing base flow but extending it out by storing this here. And so the reason that this is a good example is that this lime green is the remnant wetland vegetation, but you can see this edge where it should be all the way across the valley. And so what's happened is trails and downcutting in the system has shrunk the wetland to the center of the valley, and then where you see this kind of rusty brown, that is a juncus, a facultative species that can handle the wet dry. The lime green is the obligate wetland. It has to have wet feet. And then you lose it to the meadow grasses and grassland. So this is at Philmont Scout Ranch, which is just in the same area. It's a little bit blurry, but if you look at what this looked like in the late 1800s, you can already see the degradation. You can kind of see the cutting. The thing that I look at in all these old photographs is you can see the horse's hoof. There's probably so little vegetation that you could probably see its shoe if the picture were clear. So we're again simplifying landscapes. We're taking away the surface roughness that allows for infiltration, and we're sending water off as fast as we can. This is the process. We are looking for dispersed flow with small channels that kind of thrash around a surface. Once we get that trail or road, we get a little bit of a nick point in there. And if you see the blue line here, that's supposed to be representative of the soil water table. So as the degradation accelerates, the water table is dropping as the channel goes down. You're losing that lateral sort of flow. And so by the time you get into a really incised channel with a gully, you've lost a lot of the available water to plant roots. And so your system is really drying. So you're shooting water out of the system really fast. You're not getting a chance to expand outward and be held in the soil. So this is what it looks like up there. You have a little incised channel that starts. And if you look at this wetland vegetation, it's super green. That's super lime green. That's wetland. This channel is a little bit deeper. We're losing some of that wetland vegetation, and this is red top, which is a facultative species, so it moves in. You're starting to, even though it still looks pretty good, the landscape is drying. And then you get these huge head cuts in the system that start to fall apart. And so this unzips up, and you lose that water storage and all the soil. So this is what it looks like from above. So these slope wetlands, remember they're bathtubs with just a drain at the bottom. You start to get an incised channel that just speeds the water through the system. And you can see here too. And a lot of times the head cut will come up from a road. So this major head cut stops about right here, but then, you know, there are other factors that cause it to keep going. So this is a drying landscape. So what we're trying to do by putting these naturally based structures in, the rocks and logs, is we're trying to, we can't go back and, fill in the whole system. Let's, go to the Gulf of Mexico, get a shovelful at a time, come back up. So we're doing the best that we can to find strategic places in here to slow and sink the water. And so the permaculture term that I love is we want to take running water and make it walk. We want to take walking water and make it sit. And so we're trying to frustrate gravity in this system by putting a lot of impediments to the water. And so that's what's making it slow down, and if we're successful, to saturate laterally. So this guy right here, and you can see the lime green, intense lime green, and then the juncus, and then areas where you just even have dead wetland vegetation. So he is standing right about here. And so our goal is to take that situation, take the conditions of degradation that are chewing through the system and turn them around. So this is the degradation loop, where you have reduced plant productivity because you've reduced the water, and then you have less protective plant cover. So each blade of grass is no longer acting like a dam that sends water down into the soil. You get the reduced soil moisture, which feeds back into reduced plant productivity. You have less root growth. The plants aren't as healthy. They're not capturing as much from the sun. Reduced plant productivity, less protective plant cover, and on in this degradation loop. So what we're doing is we're just trying to interrupt this loop, and we're trying to interrupt this loop right here at the reduced infiltration. So for the land degradation, it's an interplay of the factors of water erosion, wind erosion, and the vegetation dynamics. And we've talked a lot today about vegetation dynamics. So we are tackling it from the water erosion on a small scale with structures and hoping to impact positively the vegetation, which then feeds back to the water erosion. So that's our loop there. So this is an example of one of those systems that's being chewed up. The water's moving out of the system. This is in March with snow melt. You can still see some snow there. And the water is coming over head cuts in this system, and then this is moving back up valley. This is the same year that these structures were put in to anchor the bottom of the system. And so this is at the bottom of a valley. So this is essentially, we are putting a plug in the bathtub of this wetland system. And it's not a plug in terms of being the water's impounded, but it's a plug in terms of like it's big enough and strong enough to back water back up valley. And so the hero of the story is not the structures. The hero of the story is the plant roots that you're making space for in this. And so all of these erosion control structures, natural processes, they're just gateway drugs to biodiversity, right? So the biodiversity is the important part. Like the more biodiverse of a plant system we can get up, the more disparate pathways that we can get water down into the deep soil. And so that's the goal, is to grow the plants. Don't tell Bill I said that. So we've taken this feedback loop and we've just changed it. So we've increased the soil infiltration. We're hoping to increase the soil moisture, increase the productivity, have more cover, and then increase root growth because they've got more water. They have a lot more above ground tissues so they can capture energy from the sun. They have increased productivity, and then it feeds back through. And so one of the things that Bill says in a Yogi Berra kind of way is he says, when things stop getting worse, they start getting better. And that's absolutely true. That's what we're doing. We're interrupting a bad cycle, and we're sending it on a better trajectory. And it's small scales, but still working. So one of the things that is so important in this, and this is where we can go wrong, is that we have to identify what's really going on in the system. I work with a lot of landowners, and they always take me to the absolute worst place on the property, and they say, what would you do here? That is not probably where we want to start, but we do take that worst place and then walk up valley from it and figure out why the water's moving so fast above us. And then maybe we can slow the water down and make it sit up there so that there's less force when it comes down to the really bad spot. And so what we're doing is we're trying to hit all of these things. The geomorphic, we're trying to capture sediment. The hydraulic, we're slowing the water, making it reside in the system a little bit longer. And then the ecological function, like I said, the biodiversity is sort of the end goal, because the ecosystem services are part of that great positive feedback loop. So this is an example, just a reading the landscape example from Texas. So this is a stock pond that was put in the late 80s, early 90s. This kind of bowl is probably used to be probably more of a wetland system. There's like a ephemeral creek that's close by. And you can see it's a little bit greener. And then this field, they call it the CP field. Often it's too wet to plow. So this is in 2008. And this is the perfect example of this setup. So the picture I showed you, we're up here, maybe here for some trails, but we're headed here. And you will be able to see in the next slide the drying function of having a really incised channel in the system. Okay. So this is 2012. There's a huge head cut that developed here, probably from a hole in the fence where the cattle got through and went down to the water. It moved up the fence line, and it's ripping back up through these fields. It's sending a branch up this way. So remember, this is a big green bowl, and the dark soil is moist soil, and the lighter soil is dried out. And so see where this channel goes? See how dry the soil is on either side? Because we've run the water out of the system, and it's going through so much lower that we've dried the soil completely on either side of those channels. And so think about this, like everywhere on the landscape where there's trails and roads and stuff, we are drying the systems and we are sending the water off just as fast as we can. So we're looking at the stressors. Again, the roads, railroads, trailing, modern roads, culverts are terrible. Stock tanks are usually put in incorrectly in our landscapes. They're too deep, they're too big. It creates a huge head cut that sets in motion an erosion series. And then the climate stressors are increasing. And so this is what Matthew was talking about, like sort of what are we building to? So there's a stock pond just off the screen here, and you can see that it's like, this is a heavily used landscape anyway. Every photo that I looked at on Google Earth had cattle being fed in these situations, but you can see that this landscape is just unraveling from the use patterns, from the roads, from the trails down to the stock tanks. And another thing to think about with stressors and with climate-related stressors is think about how we react to stressors. If you had 5 things to do and you were really stressed out and somebody said, I will take that one thing off your plate, it would feel huge, right? And so in building some of these structures, we're trying to reduce a couple of the stressors in the system. We can't fix everything, we can't go back, but we're reducing stressors to accelerate the recovery. Yeah. So this is Texas now, legacy stressor in Texas, 1906. So we always think everything was better before, but this goes back to what Brad was talking about. Like we used the hell out of this landscape, and we simplified it in a weird way, and then we dried it out because we simplified it, because we don't have that complexity that holds the water. And so again, look at the horse's hooves, I can see that guy's got a nick right there. There's no vegetation to cover it. So we have a long history of this. And again, does this look like a complex landscape that's ready to absorb water? Does this look like a good sponge? No. And so we over time, I think, have made our landscape a lot drier because we're sending the water off so fast. Okay. So this gets to the structures. So the erosion control and land stabilization. And so this isn't strictly restoration. Bill would like to point out we're doing a lot more stabilization. But remember what he said, you have to, stop things from getting worse and start making them better. And so this is our plugs in the system. So the stops the further degradation. So it stops that point in time of that really bad positive feedback loop. We're covering bare ground, and we're not able to do it right away with vegetation. We're doing it with site-based materials, logs, and rocks. We're creating that surface roughness. Remember, we've oversimplified all of these systems, and so until we can get the complex vegetation back, we're creating surface roughness with these structures that are hassling gravity, right? The gravity wants to take the water off as fast as it can. We're hassling it to make it slow and sit. The hydrological cycle, we're slowing the runoff and we're increasing infiltration just because we're lengthening the pathway that the water has to take to get off the system. And then for habitat improvement, the plant establishment, it has increased water. It also is a little bit protected from herbivory because the animals don't get their mouths right to the soil surface, or they don't want to walk on these rock structures. And provides a lot of microhabitat. So like if you turn over rocks in these structures, you'll find more bugs, and also snakes really like it. So it tells me that there's probably more rodents and stuff in there. Okay, thank you, Paul. So this is in Gillespie County, and this is a tiny little head cut right here in an ephemeral creek system. And you can tell that maybe it doesn't look like it's in that great a shape, but this is the areas that require the smallest intervention and have the greatest success. So the earlier you catch something in the degradation cycle, the better chances that you have. And then by the time it gets to this is an expensive problem. And your likelihood of success isn't as great because there's a tremendous amount of force. There's a stock pond above this, and all the stock ponds are put in drainages. And so this is a head cut that has been sent up from the stock pond on the neighbor's property, right, that's chewed all the way up to this one. This stock pond is probably chewing all the way up to the next one, and it's because they were built too big for the watershed, too deep. It created a big head cut situation. So again, we want to catch it early and not down here because it becomes less accessible to just landowners. Okay. So one of the structures, this is my favorite structure that we use. This is Media Luna. It's a half-moon rock structure. And we set an elevation on either side so that water doesn't tip around either end. So water backs up here, and then it's hassled going through the rocks, and it spreads as sheet flow. So this is an example on the FRP of a Media Luna that we just put in, so the water will flow this way, and then it'll be respread coming out. And in parts of Texas, there's not as many rocks, and brush is a big issue. So Juniper brush works great for Media Lunas too. This is on Andy's place at the Hershey Ranch. And so we set the ends and we did these brush Media Lunas, and even just within a few weeks, you have plants coming up under here that you wouldn't normally see because the deer would get them just right away. So a lot of times when I show the pictures of the bathtub, the slope wetlands up in northern New Mexico, people are like, This would never work here, right? It's not wet enough, it's just different. You've got the perfect situation. This is in the Chihuahuan Desert in New Mexico near Socorro. It gets about 9 inches of rainfall a year. And it has a lot of connected bare ground, so you can see that water moves off of this landscape pretty fast. And then you can see a lot of cobble at the surface, and so that desert pavement is a result of wind erosion in the system too. So we can put media lunas. This is our media luna in this system, and it's taking the flow from all this bare ground, and you can see where it's ponding water behind. And then the water is coming out in the front again is sheet flow. And so these are just like they're taking that running water and they're making it walk and sit, right? And then so they're having a much bigger effect. And if you look at the productivity of these areas compared to out here, it's huge because it's not raining more right here. It's just that they're taking the water that was leaving the system really fast and making it stay in the system longer. So one rock dams are another example of these structures. One rock dams are one rock deep. The name confuses people, but it's just one rock deep, not rocks on top of other rocks. And they're keyed together. And the goal of a one rock dam is to raise the grade of those channels so that you get more of that lateral connection. The rocks are keyed together so that each rock depends on the strength of the rock next to it so that they don't blow out as much. So if the water is coming down the hill, it's pushing on the front row of rocks, but those rocks are keyed together and pushing on each row beneath them. So it's a lot stronger than if you just dump a bucket of rocks in there. The other aspect of it is that, so if water's coming down here, it has to really work to get through these. And it slows it down enough that if it's carrying sediment from somewhere else, the water loses energy and the sediment falls out in the one rock dam structure. So if you're lucky enough to be out on the land after it's rained, you will see like chocolate milk water at the upstream end of it, and as it dumps the sediment, it's almost clear water coming out of the bottom end. And so then that provides a great place for plants to grow. So it's doing several functions at once. This is the perfect sort of Texas situation where this would be beneficial. So that's what people always ask, like, how do you know where to put these? It's not too far gone. You can tell that you would be able to benefit the area, and this area probably should be a lot more productive because you're getting water off this slope. So maybe you could put some one rock dams in that would spill some water back out. In this situation, if you were able to slow the water enough in this system, you might actually be able to drown out the dryland species that are encroaching into the creek. So this is an example of a one rock dam. And remember I talked about legacy problems and people taking you to the worst. You're not going to be able to do much about that 3 feet of bank in the short term. But remember Bill's project at Hubbell where they got 10 feet of topsoil in 20 years? You might potentially do it. You do need a sediment source. In this particular situation, we tried to do a bunch of structures above this so that hardly any sediment actually reaches this. So we are stacking all of these functions so that each one has to work less hard. And so that increases the resiliency in the system. So if one structure blows out, there's probably 3 below it that are gonna help capture. So now we're into the head cuts. This is more stabilization. If the head cut is a sloping head cut or it's only a couple feet deep, you can use a rock rundown to do it. It's basically just the one rock dam on a slope to anchor it. Go back one. So this is the kind of situation where a rock rundown would be good. It's not a huge vertical head cut. You still have some bunch grasses in there that you can work rocks around and anchor it. This is a rock rundown that's going into a big head cut. So a lot of these structures, you have the big head cut, and then you have the intermediate problem just a little bit upstream of it, and then you have the actual stressor that caused the problem upstream of that. And so that's part of this reading the landscape, where you identify the huge problem, you figure out multiple ways to remediate it above that. So this is the type of head cut that requires a structure where you probably need some heavy yellow machinery to at least deliver good microwave-sized rocks to it to anchor it. This is a structure where you'd need either a Zuni bowl or a log step fall. So this is the Zuni bowl. Zuni bowl was first used in the Zuni Mountains, I believe is why it's called that. So the water spills over this edge. This edge is half as big, so you have a plunge pool. It has a second spillover. There's a splash apron, and then you have a one rock dam below it. So just within this structure series, you have 1, 2, 3, 4 or 5 places where you slow the water down and hold it, and you've stabilized that. So this is what that looks like in practice. These are much bigger rocks. If they're not constructed properly, you can create multiple problems where there was just this one problem. So these are probably more structures that you get help with. Just skip that, please. Okay, so we did a bunch of these stack structures at the Field Research Park, and we are trying to capture water that's coming off of a petting zoo, amusement park with like lots and lots of animals in a very short, very small area, and it's all in a rain event coming onto the FRP. And so this is the top part of a project. The Good Edwards folks emptied their offices, and they sent tens of people out to move rocks to make these structures, and I think there's 13 in a series. And they've instrumented the top of this, right where all the horse manure is going to be coming in, and then the bottom of this. And so we can see hopefully the water quality differences in this little stretch. This is part of that. And so one of the most wonderful things that I've gotten to do in the last few years, working with Bill has been amazing, but the folks at the Field Research Park and the Edwards Aquifer Authority has agreed to put some science into me saying, hey, this looks better. It is a green, pretty, And so they're putting some numbers to it. So some of the structures that we've built, they've been able to instrument for soil moisture and soil temperature. So I can tell you, just because the grass is greener, that it's because of increased infiltration and soil moisture, maybe some temperature stuff, but I can't give you any numbers to that effect. And so that's what's so beautiful about the research park, is they're super thoughtful. Everybody has so much know-how, they're interested in this, and they can figure out good ways to measure and track over time. So this is a rain gauge that's right on the site where some rock structures are, and we're going to be talking mostly about this rain event in November that was just over ½ an inch. And so any questions about these slides, Michael Young's going to answer for you. So just preliminarily, they have a 10 centimeter and a 30 centimeter probes. And this is that November rain event here. And if you look at this, the blue line is where there are rock structures, treated structures, and the black line is where it's still sort of an eroded surface with bare dirt. And so we have our rain event here that you can see in this spike here. And so it appears that, we have hassled gravity in this situation, and we have a lot higher water infiltration with this bigger event at 10 centimeters and at 30 centimeters. So the interesting thing to me, and I can't answer this question, that's why Michael's sitting there, is that look at the blue line here. We have in the treated areas a little bit lower soil moisture than in the bare soil, quite a bit lower here. Look at the depth. It stays up at depth, but it goes almost just parallel here. The next slide. And so if we look at the surface, the lines are the same for a little while, and then we go back to having the treated soil have slightly less soil moisture. But at depth, this has maintained all the way till just last week. So I don't have any answers about that, but somebody will. And so then soil temperature is also really interesting. So if we were January and February here, so the soil at 10 centimeters and 30 centimeters, or they're both at 10, sorry. The treated areas have higher soil temperature for all of January. We get it mid-February, it starts to be about the same, all the way to the end of February, not much difference. And then we get to March, we get halfway through March, and then the treated areas are actually cooler. And then April, they're 4 or 5 degrees cooler all the way. Keep going. Then June and August, the treated areas are cooler still. And then we get to mid-October, we see that same pattern as in February. They're almost the same. And then it switches, and the areas treated with the rock structures are a few degrees warmer. So if we go back to me talking about those stressors, right? If somebody takes that one thing off your to-do list, it's really helpful. So we're moderating the temperature, which may not seem like a lot, but if you're a soil microorganism who has a range that's 5 degrees one way or the other, this can make a big difference. So they are changing that. Yeah. So then I've showed you like the bathtub example, so where you can see from the vegetation where the water is in the system. And in the Chihuahuan Desert, 9 inches of rainfall, you can see that it is making an impact. And so we were lucky enough, in addition to the FRP, to do a pilot project with Texas Parks and Wildlife on the Hershey Ranch in Gillespie County. And so I want to show you the Edwards Plateau, Texas example. And so in our Reading the Landscape, we have a field here, and this is an access deer trail, and they were going under the fence and a part here, and this shadow you see is a huge head cut, and then the creek actually runs this way. So they were cutting across the field to go down to this creek and cause this. And then past management had cattle in the creek pasture a lot, and so they pulled the cattle out of the creek pasture, which helped a lot, but you have these head cuts that are working up from the creek there. Okay. So this is Ryan McGillicuddy with Texas Parks and Wildlife. This was a lip project, and he's standing in the bottom of the head cut, and there's a secondary head cut here. And so it was about 4 feet deep, and this is not in a creek channel. This is just from a deer trail going down to a creek channel. And so this is the trail coming through the grass, and we set up a whole bunch of brush media lunas to remember to take the water out of the trail and respread it and respread it. And this is what it looks like after the build. So here's these media lunas, and then we used a lot of juniper on brush berms to, we're trying to slow it before it gets to the creek, before we do the big rock work. This is what it looks like 2 years later. So I want you to look at this green bubble around just the brush structures, okay? And so this is, again, those were the brush medialunas where we slowed it down. The deer were coming under the fence. As we started peeling back vegetation, you know, head cuts migrate up valley, but they send like a pilot head cut up almost. And so what's happened is the system is dried enough that whatever vegetation was there is dried out too much because the water table is dropped, and so you have another head cut. And so we had to keep working up because we found little head cut after little head cut. And you can see that this is a super active head cut because you can see the living plant roots from that year. So you're losing so much soil that it's probably migrating back 6 inches a year. The roots can't hold it. So to fix this one, we put a geotextile fabric in it, and that's important because you know the head cut's going to keep marching up valley. And so the geotextile fabric is going to let the water through, but it's going to hold the sediment behind it so that you don't get piping through a structure, because you have a lot of energy that would cause something like this. So it has geotextile fabric. And then Andy, who you're going to hear from next, gave us the choice of using oak wilt trees and cutting them and using them for the structure, or a pile of dried out cedar posts in his barn. And we stupidly chose the oaks, and we would never do that again because they're so heavy and hard to work with, and they don't grow straight. This curve is not like a camera angle, and so we had to fit each one of these logs together and then chink places where they're a little bit far apart. And log structures will raft out, unlike rock structures, and so we have to anchor them. We anchor them with smooth wire and T-posts. And you just build it layer by layer. And so this one is going to end up being 5 layers deep. And I don't know if you can see in this photo, but we have to take a sledgehammer and pound the logs back into the geotextile because that's the most important interface there. And one of the reasons we did it with logs instead of rock is because of this fence here, we wouldn't have been able to get a machine in with large enough rocks. And so that's part of what your site design will tell you. And so then, even though a lot of folks in Texas are only going to have wood to work with, it's very important to chink around the structure to smooth all of the edges with rock. And so there you had purchased rock brought in to do that. And so this is what it looks like after 2 years. And so one of the things about these structures is they are designed to go away. They're designed to do their work and blend back into the landscape and be covered with plants. And so if you want something to point to years and years later, this is not your technique. And so everything is in a series, and so the log mat, which is the analog to the One Rock Dam, below that big drop structure, chinked around with rock, and then this is after 2 years, you can't see the structure anymore because it's vegetated in. And so that means that is incrementally raising the grade of that channel. It reduces the energy from the fallover for the next event. So this is the rock rundown on top. The brush berms are on the other side of this fence. You can see it's pretty extensive coming down. This is the same picture. You can match up that tree and that tree. This is just after 2 years. We were lucky. We got some gentle rains right at the outset that brought the vegetation up between the rocks that really allowed the structure to anchor before they got any bigger events. So before, there's these 2 head cuts. We've fitted this to the landscape, and this is one of the reasons why engineers don't really like these types of structures, is because you cannot give them rectangular dimensions and depth, because these fit the need on the landscape. It's not, It's not just a geometry project in terms of like, it's always the same. So again, we slowed the water down here, there's a big head cut, and then we're gonna tackle these creek bank head cuts up here. So Andy and his wife had done an erosion control project on this creek, and none of these things are without the other. So they pulled the cattle off. They completely changed the cattle management. They were the ones that cut all the juniper brush for all of those berms. And they had previously put brush down here where it was bare, where it was a little bit, the slope was less. And so there was, and seeded, and there was quite a bit of vegetation there. And so we were able to anchor these rock structures into vegetation at the bottom. If there hadn't been the vegetation there, the rocks would have just kept rolling. So it's like a long, multi-year process that gives benefits as you go along. So this is just 2 years later, this on the creek bank head cut, where you have really stabilized this steep area with these simple techniques. So that's it. So I just want to be sure and thank the Edwards folks. It's such a tremendous group of people. The Hill Country Alliance, Daniel Oppenheimer has been a tremendous proponent of this type of work and trying to bring it to Texas. And then Texas Parks and Wildlife has done a lot to try to get the word out. And they're the ones who, pioneered getting going at the Hershey Ranch at Andy's project.
Thank you.
Thank you.
Thank you.